Hi, everybody, and welcome to Physics 252. Today, we are actually in the 5th week of class, and this model basically is up. I hope that you guys have had a chance to go through it and see the different assignments in it. We're entering a new topic. We're doing relativity this time around, okay? So let me put things in perspective for this topic. And I'm going to have a few questions in here. First of all, let me share the screen. So this is basically for this week. We have the discussion item from this week, which I'm going to talk about in here. And we also have the concepts that are covered in this week. So the concepts briefly are these transformations, Lorentz transformations, are critical and important, and there are actually two main ones for the spatial derivatives, for the spatial times, because we're taking the one-dimensional case basically, so we're not considering what happened to the z-axis and the y-axis. They stay unchanged, and we're focused just really on what happened to the x-axis and the time, because the time is not the same, okay, it changes. And then how the velocities add. Using this equations, basically you can derive these expressions. And you will see they don't add normally as the way that we have seen it in Galilean transformations. This is as opposed to Galilean transformations where the time is the same for both. Time is universal in classical mechanics. It's no longer true in this theory. And then also the transformation did not have a factor of gamma, or gamma is equal to 1 in classical mechanics. It's just x minus ut. I'm going to talk about what these things are. The other concept which is very important in terms of calculations is the Doppler effect in the case of relativity. This is how it is. The frequency is shifted depending on you, if it's positive, if the object is coming closer. This is actually a useful expression when it comes to astronomy. We use that extensively, especially in trying to learn more about the galaxies and the expansion of the universe. This is how we determined it. And also a little bit of dynamics. The main thing from dynamics is the total energy is related to the momentum via this expression, and the mass, of course, via this expression. We will use this expression extensively when it comes to nuclear physics. So it's very important that you guys familiarize yourself with it. The energy in general, which is summation of the kinetic energy, the potential energy, you can express it as the factor gamma times mc squared. Where this gamma comes from is actually comes from the two postulates of relativity, and I'm going to talk briefly about where that came about, okay, so that we have a clear understanding where everything is coming from. Two of the consequences of these things are the time dilation and the length contraction. This is the length contraction, and the time dilation is just the factor gamma also between them. So let me talk about these things in here in a little bit more detail. Before I do that, let me go back into home in here. I'm looking at it as a vantage point of a student. So this is the unit so far. We have a quiz, as typical stuff. We have lab 5, which is very important lab, and you really have to see how it's done and do it. And then this one. This is problem 70 from chapter 37. It's actually a problem in that. And what the problem is you look at Maxwell's equations and the equation that you derive off of them, which is the wave equation for optics, basically, and for light. That light is a wave and travels with the speed of c. If you apply classical mechanics, Newtonian mechanics, you'll find that this equation is no longer describe a wave. As a matter of fact, electrodynamics, physics 2, changes big time. If physics 1 is true, if classical mechanics is correct, then physics 2 is wrong. So the purpose of chapter 37 is to fix this discrepancy, and that's why relativity was introduced, to fix among other things, the fact that we have to basically reconcile these two, relativity and also, or classical mechanics in general, and Maxwell's equations. Maxwell's equations are accurate and can be proven to be so. And the problem then is that classical mechanics is wrong and it has to be replaced, hence chapter 37. So let me stop sharing and let me share briefly And I will tell you, before I do that, let me go back in here. If I open this discussion item in here, this is the recording of today. It's going to go here. It's introducing this entire topic, basically. These are old recordings. It goes in detail about the derivation of all of these things that I was talking about. And this is actually divided into 2 parts. It's a very long thing, so please take your time, including solving problems actually from this one. So you're going to go through all of these videos and look at them and basically see how things are done. But the discussion items are coming from just the first part, the top part. So these are old recordings for this same topic, okay? If you have any questions, please let me know. The discussion items are due by the September 25th at 11 p.m., which is not this Saturday, the next Saturday. So let me sleep. No, I don't mean to do that. Let me stop sharing the screen. That's what I meant to do. And let me share another screen. Before I do that, let me trigger that screen. Okay, let me stop sharing this thing first. Let me find my notes in here. And let me go into the notes and find physics 252. And here it is, and add a new item. And a new item is relativity, or chapter 37 if you wish. Okay. So let me share now my notes. Let me talk about this thing in here, what I mean by everything in here. I know this is the summary of the summary, so you're going to go through the details in there. Let me tell you the state of matter where we are. We know that classical relativity works on a day-to-day basis, basically. Somebody is jogging in a train at 6 miles per hour, and the train is going at 60 miles per hour. From the vantage point of somebody standing on the station, depending on which direction the person is jogging, if it's in the same direction as the train, that person can add the 2 velocities and predicts that the person is approaching at a speed of 66. 60 plus 6 is 66. If the person is jogging in the opposite direction of where the train is moving, then 60 minus 6 is going to be 54 miles per hour. So this is classical relativity. And basically it stems from the fact that if I take coordinate system, X, we're taking the one-dimensional case. And for an observer O, and observer O prime, which is the observer where the train is moving with a speed U, has coordinates labeled X prime. Of course, the time in here is the same. That is really the biggest thing in here. The time in this reference frame for the observer O prime, namely sitting at the train, it's with the velocity, with the train, with the times being universal. That is the key assumption that Mr. Newton has made. Time is the time everywhere. If we sync our clocks now, when the train was stationary, the clocks will remain synced forever, no matter how fast the train is moving. Okay, so the train is moving with a velocity v. So if I take a point in this coordinate system of coordinate x prime, obviously I'm looking at the same point with coordinate x with respect to this observer. Obviously, you can clearly see this distance x prime in this distance with which the train is moving at an instant t. Here it is. Let's assume initially that the 2 frames were superimposed. The origins were the same. And then the train moved. So in this case, this distance traveled by the train at that point is ut. So add the 2x is going to be x prime plus ut. Technically, it should be really t prime, but t is the same as t prime, end of the story. Okay. From the vantage point of somebody, let me find first of all the here. From the vantage point of somebody, from the vantage point of here, actually from this train, I know x prime is just going to be x minus ut prime. But t prime and t are the same. So that's why we don't really bother with this, okay? So this is basically what classical transformations is. So this is called the Galilean transformations, or classical relativity, because I can take the derivative of this expression and find v in the non-moving frame is equal to v prime plus u, because t and t prime are the same. So if you wish to take the derivative with respect to t, that's what v is, dx over dt. You say dx prime over dt is the same as dx prime over dt prime times dt prime over dt. That's the chain rule. And this is 1 because both of them are actually the same quantity, classical mechanics. And this is v prime. And the same thing, du t prime with respect to t is du with respect to t prime times dt prime with respect to t prime with respect to t, and that's 1 too. So that's going to be u. So this is exactly what I was saying in here earlier. Okay. So if you happen to be moving in the same direction as the train is moving, with 6 miles per hour, and the train is moving 60 miles per hour, according to this expression, 60 plus 6 is going to be 66 miles per hour for an observer sitting outside looking at it. This is classical mechanics. The trouble, as I was saying in here, if I look at Maxwell's equations, let me remind you what Maxwell's equations are. Let's write them in free space. The divergence of the electric field is 0. Technically, usually it's rho over epsilon naught, but I'm taking them in free space. Okay. The divergence of the magnetic field is always 0 because the magnetic field always curves, never diverges. There are no monopoles, basically. That's what it is. Okay. Otherwise, you're going to see the magnetic charge times mu naught or something else. Okay. And then you have the curve of the electric field, which is given by the Faraday's law, really. And Faraday's law says the circulation of the electric field in this case is going to be proportional to, there is no mu naught or anything like that, I'm sorry, to the rate at which the flux is changing with time. And that is going to be actually in differential form, the partial of t, of b with respect to t. And then finally, Ampere-Maxwell's law gives me, and there is a minus sign due to lens in here, you guys remember from your physics too. And in here, it's going to be mu naught, epsilon naught. This is the displacement current times the electric field. And here, the rate at which the electric field is changing. Obviously, J is equal to 0 in here. Technically, I'm supposed to add to it mu naught J, but I'm in free space. In free space, there are no currents and no current densities. So there is no, I mean, no charges and no current densities. So in other words, we are away from the source. So if I write these equations and take a direction of polarization for light, specific direction, and let's say, for example, direction of propagation is in the x-axis. So anything with respect to z and anything with respect to y is 0. There is no y and z dependence. And in this case, immediately the first two equations will give you bx and ex equal to 0. Okay, they come from that expression. In other words, the electromagnetic wave in free space is going to be perpendicular to the direction of propagation, which is the x-axis, by the way, because the other two derivatives, I'm assuming that it doesn't. In other words, I'm looking at the planar solution. That's what you did in physics too. I'm just reviewing these things with you guys. So at the end, the equation that the other two components satisfy. As a matter of fact, I'm going to take a polarized beam because I cannot have an EX component. So the only possibility I can have an EY or an EZ or a combination of both. So what I'm going to do, I'm going to polarize it in a specific direction. Let's take the direction in the Y direction. So E is going to be in the Y direction, period. And the same thing, B then, as a result of the other equations, is going to be actually in the Z direction. Okay, end of the story, okay? So this is basically where we are in terms of everything. And let's try. And once we put all of the equations together and take the derivative of this one with respect to x, or both of the terms in here, whether ex or e. By the way, this is function of both x and t now, and this is function of x and t, okay? Once we have that, we will find the second derivative of both E or B. Doesn't matter. In that polarized direction. Of course, if I take a non-polarized beam, I'm going to have the components also satisfy this equation. So there is no loss of there is no loss in And generalization in this case, I mean, when I take a polarized beam, so everything is true for a polarized and non-polarized beam. So it's going to be the second derivative with respect to x, of course. I have to be careful in here. So minus the second derivative of e. I'm taking the ey as e, okay? Just dropping the symbol in here with respect to time. And then I have a scaling factor in here, okay? And that scaling factor turned out to be exactly mu naught times epsilon naught. That is what c squared is, okay? We say then that the solution in this case was a wave. And we have the speed of wave, which is just the square root, the inverse of 1 over the square root of mu naught epsilon naught. It turns out to be 300,000 kilometers per second, okay? And we have description of this wave. We have everything. We have the harmonics, and we have the different colors coming from different frequencies, and the dispersion law, which is a critical relationship that emerges off of this. The wavelength and the period are related to one another through this expression, and the frequency, if you want to write it in terms of the frequency. No, I write it backward. Yeah, c equals to lambda f. Okay, that's wrong. Okay, you guys paid that, grabbed it quickly. Okay. So that is a dispersion law. That is how the frequency will be. So all of this discussion is beautiful and led us to all kinds of optics and things like that. Well, this equation is a problem for us. This entire electromagnetism is a problem if this is true. If Galilean classical mechanics is true. So we needed to fix that. We needed to fix classical mechanics, if you wish, to be compatible with this equation. This equation becomes variant, becomes non-invariant under classical mechanics transformations. And we have to fix that. That's what we were toward the end of the 1800s, toward the end of the 19th century. So Mr. Einstein proposed the following, that there is something the matter with classical mechanics we have to fix, okay? One of the consequences of this theory, actually, classical mechanics, I mean, electrodynamics or electricity and magnetism, trying to reconcile it with classical mechanics, is to explain the high value for C, because this number C is big, 3 × 10⁸ meters per second. And if we compare it to sound, for example, this is ridiculously big. And if we compare it to anything that we know vibrating, this is ridiculously big in mechanics. And we know that this speed has to do with the stiffness of the medium. So this medium must be super stiff to produce this where these waves are propagating. So what looks like it's vacuum between us and the sun must be a medium of tremendous stiffness. So we decided to find the velocity of the Earth with respect to this medium, which they call it ether. So Mr. Michelson and Morley devised an experiment, and actually other experiments later on were devised after that, trying to find the speed of the Earth with respect to the ether, and we found none. The Earth does not move; nothing moves with respect to the ether. So that was a big problem. So we had a problem with classical mechanics big time, reconciling what we can see and measure and what these equations are telling us from electrodynamics, from electricity and magnetism. So Mr. Einstein thought of the problem and solved it in the following way. 2 hypotheses. And the first hypothesis is the fact that the law is still valid. Doesn't matter which observer you are on. By the way, this is called inertial observers. This observer and that observer are called inertial observers. Why is that? Because the physics, according to classical mechanics, does not change. Because we got up to the velocity in here is equal to v prime plus q. But if I take the derivative, the second derivative of this one, that gives me the acceleration is equal to the acceleration prime plus the derivative of a constant. Remember, I assumed u to be constant. This u is constant. So then the derivative of a constant is 0. So the accelerations are the same. So if I tally the forces in one on the object, here is the object, has one force, the second force, and everything else, and it has a mass m. So I can say F equals to ma in the old frame, or I can say F is equal to ma prime in the new frame, because A and A prime are the same. So physics should not change. That's the whole purpose of this this thing. In classical mechanics, they did not change in this frame of reference. So Mr. Einstein said the same thing must be true. So there is no experiment you can do that can tell you are moving in the train or the earth is moving. Because as far as you're concerned, you're sitting in that train, you're sipping your coffee. There is no objection on the fact that maybe the train is sitting still and the tracks and the earth and the cows and the trees and the mountains, somebody is dragging them on the other outside with the same speed of 60 miles per hour in the opposite direction. There is no experiment that should convince you otherwise. I mean, the only reason why we don't believe that scenario is because of a cultural bias. That's all, because we think that it's impossible somebody does that. But if somehow the earth, while the train is sitting on its tracks, spins in the opposite direction at 60 miles per hour, and you were sleeping before it took off and did that, there is no way you can do an experiment and find out if really you are the one moving, the train moving at 60 miles per hour, or maybe the opposite is true. Because let's say, for example, the projectile, you throw a projectile upward and you measure how far it's going to go up and down, or how long it takes to go up and down. You do that, you're going to find a time, whether for this observer or the other observer, because both of them satisfy F equals to ma, and hence both of them will need the same time. So in this case, you're not going to find out. However, if these equations are true, and if these equations for light are true, and you do transformation under these equations change shape and the frequency is no longer the same, or the wavelength is not the same, or the speed changes. So for you to find out if indeed you are on a train that is moving at constant speed or the other way around, all you have to do is just check the light. If you're expecting a frequency, you're going to find something else. Or if you're expecting a wavelength, you're going to find out something else. So if the speed of light, you're going to find something else. As a matter of fact, that's how you're going to test it. But of course, there is no experiment that even in light that can do that. This one still do not change. They should not change. The physics of electricity and magnetism should not change too. It should need to stay the same for both the person sitting in the station and the person sitting in the train. Hence, Mr. Einstein had to state the first postulate is that there is no experiment that can resolve which of the observers, inertial observers, condition, okay? Observers is moving. This is the principle of relativity, that physics must be the same for all observers, okay? This is what this tried to do, but it failed here. And it failed also with the ether, and it failed with other places too. Okay. The second postulate, and this is actually another thing that we can do. Let's say, for example, when these two observers were next to one another, when the two observers, the two origins were on top of each other, basically before, when the train passes by the observer. At that point, we sync the clocks, okay? Make sure it's 12 in your clock, make sure it's 12 on my clock. Bang, we hit them. And then in the same time, we'll fire a laser beam. Laser beam travels a certain distance. I measure that distance and I tell you how much time it took. So I can find the speed of light, which is just the distance over time. But since you're moving on the train, the observer who is moving on the train has a special velocity u that is moving on the train, and fires the same beam, is going to measure difference because the displacement, that event where it hits is going to be a different location. X prime measures different location, and the clock now need to be different because there is every experiment that you can think of, light is the same, does not travel with different speeds depending on the observer. So the speed of light is independent of that the observers. That's the second principle. the speed of light is a universal constant for all inertial observers. This is assignment number 1 of the discussion item. By the way, problem 70, the solution to it goes in extensive detail about proving the fact that Galilean transformations, they change this equation. This equation becomes non-invariant in it. This equation changes shape, and there will be a bunch of cross-term derivatives in it, okay? Please follow that calculation, because actually it's a homework problem too, okay? And then it takes the Galilean, the Lorentz transformations that are derived from these expressions, and then checks, and it finds that these equations are actually invariant under it. That's actually part of the thing that Mr. Lorentz has done extensively. He wanted to find transformations where these equations of classical of electricity and magnetism are invariant, and that's what he found, independently of the work of Mr. Einstein. Mr. Einstein took it from there and basically came up with his theory to work out the theory of relativity. So there was a lot of benefit from Mr. Einstein for the work of Mr. Lorentz. Mr. Lorentz became the first #1 proponent of relativity because of the fact he was a mathematician, of course, and did a lot of work in other fields also in mathematics. So it's an interesting thing to follow the story in that. Anyway, let's follow these 2 principles and see if we can derive Lorentz transformations. Because Lorentz transformations, some books, they're used as actually a hypothesis or some sort of a postulates. And the 2 postulates of relativity are only these 2, okay? So they're actually derived concepts from there. So let me explain what I mean by the problem, okay? Let me restate the problem. Let me go back to the experiment of the light that I mentioned. Here is observer 1 and observer 2. And I'm drawing this one in the so-called Minkowski representation, where time is on the y-axis and the position. This is a one-dimensional problem, by the way. And this is x prime axis. This is observer O prime. This is observer O. And this is the t prime. I'm allowing for t to be different than t. And it's going to be, and I'm going to argue why that is. When we were together, when the 2 observers were together, they sync the clocks. And then they fired a beam. The beam started from this location from both observers. From this vantage point, because he's moving with the observer, it started from here. But they started when they were together, okay? And it traveled for this guy from here just to this point, x prime. For this observer, it traveled the distance the train traveled, which is ut, and then x prime. So they traveled the whole distance x. That's what this person is measuring. And of course, it took an amount of time t to do that. For this one, it traveled from this origin, as far as concerned, because its origin itself is moving with the train. So in this case, it took an amount of time t prime. Since both observers, according to postulate number 2, must measure the same time, the same light, the first one can swear that the light is moving with the speed c, so that this equation is true. In other words, the speed of light is equal to x over t. The second light says, the second observer, O prime, says, no, it's actually x prime is equal to the same speed, which they must measure both of them according to the second postulate, but at a different time. It took less time to do that because traveled less distance, and this speed is x over t prime. So there is a conflict now. The first one tells the second one, hey, your meter stick is wrong. Your meter stick is too long. And your clock is moving too fast. Or too slow, I should say. Okay, it takes all of this time. Okay, where a large number here and a large number in here, the ratio did not change. The other one say, no, wait a minute. There is nothing the matter with my the meter stick, because they compare it to the standard meter stick, and the clock is, everything is beautiful in here. I think the meter stick that you're using is too short, and the clock is moving too fast in your or too slow in your reference frame. So that is really the conflicts in here that we have in here. So in order to allow for that to happen, we're going to use a tinkering factor in here, a gamma factor. Let me explain what that is. Do not confuse gamma with CP over CV. This is a new factor that you're going to be called Lorentz factor because people called it this way. So I'm not going to change it. And that's how the textbook calls it too. Okay. So for this observer, X, of course, it's clearly equal to UT plus X prime. At least it looks like from this geometry. But to account for the tinkering with the scales, we have to account for that. So what I'm going to say in here is X is actually equal to this factor, the fudge factor, if you want, is just X prime plus, since I'm in the M prime frame, so I'm going to use actually the T prime in this case, okay? So give me your X prime and T prime, I can find you where the position is in X and T. For the other observer, no, actually you are moving away with the velocity U in the opposite direction. So it's going to be X prime is equal to gamma times X minus UT, okay? So this is, if you wish, prescription on how to move from primed to unprimed and vice versa. Okay? From one frame to the other, from the observer O to the observer O prime. So this is basically transformations that we need to satisfy. Gamma has to be the same. Because if I accuse you of something, I can accuse you of the same thing. So the tinkering factor needs to be the same thing. So if I do that, then I'm going to, one of the ways of finding this gamma is to do the following. Multiply these equations side by side. X prime is equal to gamma squared, of course, times. One of the issues that we have in here for this gamma, since it has to be a rescaling factor for both the meter stick and the time and everything else, this cannot be dependent. This cannot be an odd function of V, because of the fact that if it is, then this equation will change sign, okay? The meter stick now will reverse. So it has to be an even function at best with respect to the velocity. And we're going to show that it is. So I'm going to multiply side by side. Well, X times X prime is X prime. X prime times UT, so it's minus UT X prime. And then I have X times UT prime, so it's going to be UXT prime. And finally, I have UU, which is negative U squared TT prime. Okay, so that's basically what this thing says. This is true all the time, no matter which event you're looking at. There is a special event I mentioned earlier when the two reference frames were together, we fired the beam. And that is a special event because it involves light. Actually, you find a beam of light that moves at speed c. So we know this relationship is true for that specific event, which has a universality of light. So if it's true, in general, it's true for that special case, which is actually an important case involved light. So we know that X is equal to CT, and we know that X prime is equal to CT prime. If I multiply these two expressions in here together, I will find that X times X prime is equal to C squared times T prime. So what I'm going to do, actually, I'm going to mirror a sub X by CT, and I'm going to sub X prime by CT prime everywhere in this expression. So what I'm going to find in this way in here is that it's going to be C squared times TT prime is equal to gamma squared times X times X prime. It's the same thing, C squared times TT prime minus U times T times X prime. Well, X prime is CT prime, so there is a C times TT prime, okay? Plus U times X. X is a CT, so it's going to be CU TT prime minus U squared TT prime, and that's it. Well, these two terms cancel because one of them is positive, the other one is negative, and the TT prime is everywhere the same from both sides. No, this is the term doesn't involve this term. So at the end, I will find C squared is equal to gamma squared times C squared minus U squared. In other words, the expression for gamma is just C squared over C squared minus U squared. And if I reduce it a little bit further, I can find the expression in here. The way I scale the parameters in here is U squared over C squared. This is a factor gamma. Now I have transformations, okay? It has to be the positive value because the rulers and the clocks are positive numbers in here, okay? So at the end, so when I take square root, it's just a positive value. So let me look at the again, because those are just what it is. They are just to play with the ratios of these things. So let me go back into the expression x in here. So what I have found is x equal to x prime plus ct gamma times x prime plus ut prime. And I have found that x prime is equal to gamma, where gamma is this expression basically of x minus ut. So it'd be nice if I can express also t prime in terms of x so that I have really put the derivation for that. So what I'm going to do, I'm going to take equation 2 and move it over to this form and write x prime plus ut prime is equal to x over gamma. All I did was divide by gamma this entire expression and rearrange this expression so that it's equal to, well, I know what x prime is. It's this factor. So it's going to be gamma times x minus ut plus ut prime is equal to x over gamma. It's a matter of algebra now. We're trying to find t prime in terms of t and x, because we have already x prime in terms of x and t. So we want just now the opposite. T prime is a function of x and t. So all I have to do now is divide everywhere, or leave it as is for right now, but move this to the other side and take gamma as a common factor. So I will have ut prime is equal to gamma as a common factor, open parentheses. So I have a negative x over gamma squared, okay? That's, oh, positive, I'm sorry, I didn't move it. So it's say x over gamma squared, but in here I will have a negative x, positive ut, okay? We're almost there, okay? Divide everything by u, and it will have u and u canceling. So it's going to be t prime equals to, first of all, gamma times open parentheses. I have u and u canceling, so I'm left with t. And I have 1 over gamma squared minus 1 divided by u in this case. So I will have 1 over gamma squared minus 1 times x over u. I need to find what this expression is. Remember, gamma squared is equal to 1 over minus u squared over c squared, meaning that 1 over gamma squared is actually equal to 1 minus u squared over c squared. That's all. Okay. Minus 1, so 1 over gamma squared minus 1. This one cancels, and I will be left with minus u squared over c squared. And I have a u in here, and I have a u squared in there. So they cancel, and I will be left with the final expression for t prime, which is gamma to open parentheses of t minus u. Remember, one of u squared cancels the u in the denominator over c squared times x. In addition to x prime is equal to gamma times x minus ut. So these are the Lorentz transformations. If you're worried what happened to the z and y, well, they stay the same because we took one-dimensional case. So these are the Lorentz transformations. I urge you guys to go through the rest of the derivations because they're interesting derivations where you're going to discover all kinds of properties in here. One of them that you're going to find is, as I was saying, is the expression for the energy. First of all, the rest energy is written as mc squared. So this is sometimes called the rest energy or the energy of rest. Okay. And this is an important expression in here. In general, it's actually gamma. The total energy is gamma mc squared. Okay. Where this gamma is the same factor as I was talking about in here, in there. And in terms of the momentum is actually going to be written as equal to mc squared, the whole thing squared. Of course, this is the total energy plus the part that is coming from the momentum contributions, okay? Another thing that is going to be important in here, I know this, I derived it, at least in the lectures, was somewhat of an kind of a, I mean, I followed the book, but honestly, it's not really a good derivation because it starts with the definition of the momentum as being some sort of a vector gamma mc. mv, I'm sorry, okay? And you follow that derivation and you find it. But this is actually misleading, because in relativity, one of the things we abandon is the 3-vector representation. And we have to really use the 4-vector representation in this case. And the momentum would be a 4-vector momentum, and the whole dynamics changes. Since we are not ready for that type of algebra, I follow that kind of somewhat basically half derivation, if you wish, to arrive at the expression for the energy, for the kinetic energy. Okay, the answer is correct, but honestly, the derivation is not solidly built. And because there is a problem in here, this expression in here has V in it. So it has V in it. I'm taking a particle in here. So we're asking what happened to the U? Why are you using V? Well, because I'm taking proton, for example, and the proton is moving in a specific direction. Now, that is, it has its own reference frame, and it's moving with that reference frame since it has a velocity V. So now its velocity is U, okay? That's one thing. But assume that the electron somehow accelerates or gets into a collision or something, the proton, now you have a problem because the velocity is changing with time. Which velocity are you going to plug in here? If the object is moving in all directions, like in a Betatron, for example, the one that you saw in physics 2, well, we have a problem because the velocity, at least on a two-dimensional surface, has an x component and a y component. And now when you're looking at this momentum, it depends on all the parameters. So now we're taking the derivative with respect to those terms. You're going to have an issue because the force will not be proportional to the acceleration. So classical mechanics starts to basically does not make sense already. And it doesn't make sense. One of the things is because of this vector that I defined in here. It's not really a proper vector. It has to be really a 4-vector, okay, to really properly treat the signs in here correctly. Mind you that the relativity usually is done as part of a big course that just dedicates itself to a relativity, and it requires a lot of mathematics that we're not doing a lot of it in here. So we're doing basically skimming the surface in here as far as this thing. Now, this is an important concept. And the other thing, as I mentioned before, is the Doppler effect. And the Doppler effect, the consequence of it. So basically think of the following scenario. You have a source that emits a wave. That wave is traveling with its time. One of the two consequences that I mentioned is the time dilation and the length contraction. And those are coming directly from Lorentz transformations. And they have to be. Remember what I was talking about, you don't agree about the meter stick and we don't agree on the clock. So that is actually the consequence of those things. That's the speed has to be constant. Furthermore, the speed cannot be greater than the speed of light, because if you look at the expression gamma, gamma has square root of 1 minus something. That something better be less than 1. So the speed u can never be greater than it's always less than c, actually, okay? And in special case, only for the case of light, it's equal to c. You have to have a particle that does not have a mass to satisfy that condition, and photon is one of them. Gamma is an interesting property in here. Let me try to plot gamma in here. But before I finish that, let me talk a little bit about the Doppler effect in here. So because of the length contract, because actually of the time dilation, the source has a certain built-in frequency f naught, period t naught. And the perceiver in here will measure a frequency t. And because of the fact that the source is moving with a special speed u, so at the end of the day, if you do the algebra, you're going to find the measured velocity or the perceived frequency is going to be shifted based on the ratio of this velocity and that of the speed of light. This is slightly different than the one that you derived from physics 1 for sound. Physics 1 from sound gives you an expression that does not involve the square root, and there is no numerator in it. From physics 1 for sound, if only the source is moving, then in this case is equal to 1 over 1 minus u over c, where c in that case is the speed of sound, not the speed of light, because it's only sound. So that's what is the case for the case of sound. But in this case, because of the time dilation, there is another factor in the numerator that accounts for that. And that is basically, that is the gamma factor. And that is where the square root is coming from in here, okay? So this is the difference. For some, it's still true. But if you're going to use a laser beam, for example, to try to trap people, for example, on the freeway, so you use a laser, for example, for police officer to stop you, it's still true because your speed is very small compared to the speed of light. So they can use, for example, the classical expression, and it should work fine. But for example, for a galaxy far away that is moving super fast, then that expression will be a problem because you're not going to be using classical mechanics. You have to use relativity, and you're interested in the shift in the frequency for a specific wavelength. For example, for hydrogen, which is the main components of most of the material in the universe anyway. So if there is a special line that you're interested in, and you find it shifted by an amount, and you find the shift where the frequency need to be, but it's in here. So you find delta F, which is F minus F naught. And if you divide that by F naught, you're going to find the relative shift between these two. Well, it's in here. It's in this expression. It's going to be square root of 1 plus u over c minus 1 over c minus 1, okay? Depending on how fast the galaxy is moving, you're going to find the shift. If it is shifted toward the blue, then it's coming toward us. If it is shifted toward the red, then it's shifting, then it's moving away from us. That means u is negative. So this will become a negative, and this will become a positive, and the frequency will be less. So it's shifted toward the lower frequencies, which is the color red. So in this case, you say that the galaxy is receding away from us, and the universe was expanding. This is how Mr. Hubble discovered the expansion of the universe. Well, all kinds of interesting stuff in here. This is a summary of the summary. You are still responsible to read those questions. The videos I showed you earlier, they're in the summary in there. And go through the derivations. Hopefully, if you have any questions, please let me know. Hopefully, everything will be clear. And there is actually item 1 of the discussion was this one, put the laws of the two postulates in your own words, because I really want you to be familiar with them and how simple they are and how powerful they were to basically yield to a brand new physics. The other thing also that I want you to be at ease with, and I already provided you with a solution to it, is to actually go through Maxwell's equations and show that indeed they are invariant in these transformations, okay? So that's you must do. In addition, there is a problem session down there in the bottom that I want you to focus on and do those problems again. In terms of the exam, which is going to be next week, is going to focus on chapters 17, 18, 19, and 20, only the 4 chapters. The review problems, they're actually on Canvas. All the problems that are solved actually in the discussion items in there, in addition to whatever homework problems you have in there, okay? So if you guys have any questions, please let me know. I'm going to stop the recording right now, and please reach out. Thank you.